In this video, we're going to be talking about higher order derivatives and also inflection points, concavity, and their interpretations. So to start off, what is a higher order derivative? Well, a higher order derivative is, let's say you have a function, right? 4x to the power of 3. Well, a higher order derivative isn't the first derivative. So the first derivative of this is using power rule is 12x squared. The higher order derivative is the second derivative, hence the 2 primes, which we'll be talking about notation on the next segment of this video. But the higher order derivative is just if you take anything past the first derivative. So you get 24x here. Basically, you just need to take the derivative of the derivative, right? I just took the derivative of 12x squared to get 24x. And if you want to go even higher, let's say, if you wanted to go even higher, you would do f triple prime to get the third derivative, and you get 24 here. And if you get the 24th, if you take the fourth derivative, you get 0. So basically, higher order derivatives is just the derivative of the derivative of the derivative. Just take derivatives of your derivatives like a normal function. Don't treat your functions differently just because they're a derivative of something. So let's move on to notation. So some notations look like this. This is called the Leibniz notation. So d squared dx squared is your function for your second derivative. So this is also equal to f double prime. So you'll see 2 primes here. And this is also equal to y double prime. As your function of x is equal to y, you can just write 2 primes on both of them. Now, if you wanted even higher order derivatives, you would use d3y over dx3 is equal to f1, 2, 3, right? More primes. 1, 2, 3. But if you wanted to go even higher, some people even start at 3 when they're using this notation. But let's say you wanted the fourth derivative. Quite useless, doesn't really describe much in my knowledge. So you won't be doing much of the fourth derivative, nor the third derivative in your calculus class. But the fourth derivative notation looks like this. So you're going to have a parentheses 4 rather than 4 primes, because eventually you're going to be like, okay, I'm tired of writing these quotation marks and I just want to write down a number instead. And you're going to see y4 as well. Now, of course, don't confuse this y4 as y to the power of 4. If it's in parentheses like this, and y represents some function, you can assume that it's some higher order derivative. And likely the problem, if you're doing anything, will state if you're referring to a derivative rather than y to the power of 4. But what's really important is the second derivative. So these other derivatives, completely useless. I did not use them in slightest time in my class. You might use them in calculus 2, but in calculus 1 you're not going to be really using them. Not might use them in calculus 2, you will be using those in calculus 2 actually. But let's talk about the second derivative and how you can use it to graph functions. So let's talk about concavity right now. So let's say there was some function, some wavy function. Alright, and the domain isn't limited to the picture, so I drew arrows on it. This is the y, this is the x. And this function had things called, or properties called concave down or concave up. And these concave down and concave up can be represented by and can be calculated using your second derivative. So what is concave down and concave up? Well, if I were to separate certain parts right now, you can tell that this part of the graph is curving down. Now, what does this curving down have anything to do with the second derivative? Well, the first derivative, right? The first derivative describes a positive or negative slope. So the first derivative can describe the slope of the tangent line. So right here, the first derivative is here is negative, since the slope of the tangent line is negative. And the first derivative here is positive, right? Since the slope of the tangent line is positive. But what does the second derivative tell us about our graph? It tells us a very important thing called concavity. So when something is concave down or kind of curled down like this, it has a negative second derivative. And when the graph is sort of curled up like this, it has a positive. Now, you're not always going to have functions that are prettily curled like this, right? You're going to have some things that look like exponential functions. So exponential functions aren't perfectly curved, but this is still considered concave up. So for exponential functions, the entire thing is concave up, right? All of these are curved up. It sort of represent, it's sort of like a cup, sort of the cross section of a cup. And right here is also concave down, right? So this has a negative second derivative. And right here, between these 2 points right here, kind of here, this is a positive concavity. So this is concave up. And right here is sort of concave down, which is negative. Now, these points where the concavity switches, so the points where the concavity turns negative to positive, are equal to, sorry, not equal to, what am I saying? Are called inflection points. So inflection points. And an inflection point is when the concavity changes. So when something turns from negative to positive, or concave up to concave down, or concave down to concave up, that point in which the concavity switches is called an inflection point. And you can calculate the inflection point, right, the inflection points, by setting your second derivative equal to 0. So when your second derivative is negative, the function is concave down, and when your second derivative is positive, the function is concave up. So in order for a number to switch from negative to positive, you need a 0 in between it, right? You can't just go from negative to positive without touching 0 somewhere. So let's say what's it called? The intermediate value theorem states that. Now, don't just think that when your second derivative is equal to 0, you're going to get an inflection point. Remember, inflection points are only when the concavity changes, so only when the second derivative changes from negative to positive. So for the function, let's say for the function, drawing the graph, for the function x to the power of 4, all right, equals your function. You could take your second derivative, and if you take your second derivative, you'll get 12x squared. I'm just skipping some steps here. But when you take your second derivative, you get 12x squared. Now, if we draw just the x to the power of 4 graph, you might get something that looks like this. Let's use red, since I use red to draw graphs usually. You might get something that looks like this, right? Kind of a parabola. A little flatter at the bottom, though, than a normal parabola. But at 0, so when the second derivative is 0, x is equal to 0, right? So right here, x is equal to 0, and f double prime of x for 0 is also equal to 0. So if you plug in 0 for your function, you also get 12, 0 to the power of 2, which is just 0. So although your function's second derivative is equal to 0 at a certain point, at both of these locations, to the left and to the right of x equals 0, your function is concave up. See, these both are cupping upward. So this is concave up. Now, you might be wondering, okay, well, how can I tell if there's an inflection point? You just need to plug in the numbers on both sides of your x value. That's at 0. So if you want to test if there's an inflection point, plug in some number to the left of x, like x equals -1 and 1, and see if both of them change. So if you plug in x equals -1 into your second derivative, you might get some positive number, right here, for this function. And if you plug in 1 for this second derivative of our function, you'll get another positive number. So if these signs don't change on either side of your x equals 0 point for your second derivative, then you don't have an inflection point. So all in all, higher order derivatives really aren't that bad. It's all about the interpretation, and once you get a grasp of the interpretation of a higher order derivative, like especially the second derivative, you can use the second derivative to do a lot of things like graph, tell if a particle being represented by a function is speeding up or speeding down using your derivatives. And you can also tell if something is a local max or local min You can tell if a point is a local max or a local min using higher order derivatives. And I'm going to have videos on all of that if you guys are interested. But as always, if you have any questions, put it in the comment section. Thanks for watching.